All right, we are going to look at what happens when a water reacts with a hydrocarbon. Now, it's important to recognize that it's actually alkenes that will undergo this reaction with water. And that's because alkanes are actually really unreactive. So, our alkenes are going to undergo a reaction with water, and it's called a hydration reaction. So we're going to look at just the simplest alkene that exists, our ethene, very close to the ethane, just different by a double bond. And our ethene is going to undergo a reaction with water. Now I'm going to draw water a little bit differently than what we've seen before, but we do know that our water is an H2O, and sometimes we can draw it like this, HOH, just to help us see where the different parts of the water molecule is going. So what happens is the double bond that is involved over here in the ethene, actually those electrons actually shift and they come here. So the electrons in that double bond are going to shift and they're going to come here. They come here. So the hydrogens that are already bonded to the ethene, they kind of make some space. They move. And this is because of a theory called Vesper theory. We haven't talked about it yet, but it basically says that electron pairs spread themselves out as much as they possibly can because they repel. So two negative charges repel. So those hydrogens kind of spread themselves out and make some space. Now, this bond connecting the carbon still exists. And what happens is those electrons that shifted from the double bond end up being used to attach one of the hydrogens from the water. Now, we have to remember too, I'm just going to draw this down here, that the hydrogen was being attached to the oxygen with a bond. I'm just going to write out our water to look like this. And those electrons being used to attach the green hydrogen come over here and they get used to attach the OH to the carbon. And because that carbon has another pair of electrons bonded around it, the hydrogens kind of shift over and make some space. Okay, so this is all a hydration reaction is. It's when water reacts with an alkene and we end up with this this group right here, this OH group attached to the hydrocarbon. Now we're going to talk more about this OH group later, but when an oxygen and a hydrogen are bonded to a hydrocarbon, it's called a hydroxyl group. Just going to have to bear with me. My stylus has got a bit of a lag, so it's not doing so great. Okay, so this hydration reaction actually needs a little bit of a helper. It needs something called a catalyst. So it's going to work best if it is occurring in a in a sulfuric acid catalyst. So an H2SO4 catalyst. Now, a catalyst is just something that speeds up a reaction. It's not used in the reaction. It's not part of the reactants or part of the products, but it speeds things up. Maybe I'll label that. I'm running out of colors. Catalyst. Just write this down here. So, in order for this hydration reaction to occur, it needs to have the sulfuric acid catalyst. So the reason we looked at this is because I wanted you to understand how that oxygen atom was getting bonded to a hydrocarbon. And we're going to focus now on what this oxygen atom is doing to the properties of our hydrocarbon. So if you think back to some of the work that you've already done, you've compared some properties of ethane and ethanol. Right. So our ethane, we're going to scroll up here. Okay. So actually, the last thing I want to add, I think we'll name these guys. So remember that this is our ethene. It's got that double bond in there. And over here, we can't name this just ethane, even though it's just single bonds, because you should know by now that we have to name a molecule based on everything that's bonded to it. So this becomes, because it has a hydroxyl group on it, it becomes ethanol. And we're going to talk more about this later. I just want you to recognize that it's the hydroxyl group that results in the ending "ol" on the molecule. Okay, and this is a special organic family called alcohols. And again, we're going to kind of get into this organic family a little bit later. But for now, I just want to focus on what that oxygen atom is doing to the properties of our hydrocarbons and why. All right, so how does the presence of this oxygen atom impact our molecule? And I've drawn out our ethane molecule and our ethanol molecule here. And I just want to point out that I've drawn my hydroxyl group this way because that hydrogen is really bonded to that oxygen, and we're going to focus in on these bonds. So if we could zoom in, we're going to zoom in. And if we could zoom in and look at what's happening here with our carbon and our hydrogen, we're going to come down here because we know from previous science, that what's really happening is, even though we draw our bond to look like this, what's really happening is the carbon and the hydrogen are sharing some electrons. So these are electrons. We know to make our covalent bond that the carbon and the hydrogen are sharing electrons. Now, when carbon and hydrogen share electrons, they share them equally. The electrons are exactly in the middle between carbon and hydrogen. And that's really important here. It's important because something different happens when our carbon and our hydrogen, or our carbon and our oxygen, bond together. So when carbon and hydrogen bond, our electrons stay in the middle, in between carbon and hydrogen, and the two atoms are sharing the electrons. So this is, again, our traditional, what we've known before as a covalent bond. The electrons are shared between two atoms. Now, if we were to zoom in on what's happening between the carbon and the oxygen, so we're going to bring this down here, we're going to see something different. Now, again, our carbon is still covalently bonded with our oxygen. And we would expect that, again, the electron pairs hang out in the middle. But this is actually not the case. So these two electrons, they're not in the middle. They're actually closer to our oxygen. So in the case between our carbon and our oxygen, the electrons are closer to oxygen. This is because, so they're closer to oxygen. So they're not shared equally in the middle. It's an unequal sharing. The oxygen gets the electrons more than the carbon. It's like the remote and my husband and I. He gets the remote a lot more than I do. So what we know now, if we look at this, there's actually two kinds of covalent bonds. There's the kind over here that's happening between the carbon and the hydrogen where there's equal sharing of electrons. And then there's also situations where there's unequal sharing of electrons in the bonds. So when the electrons are shared equally, it is called a non-polar covalent bond. And this nonpolar covalent bond happens because both atoms attract the electrons equally. So you can think about it as a tug-of-war team. The carbon and the hydrogen are equally matched tug-of-war teams, and the electrons just stay in the middle because neither one of them are strong enough to pull the electron closer to itself. So when we have this this unequal sharing of electrons over here, this is called a polar covalent bond. Just gonna square polar. So this polar covalent bond occurs when one atom has a stronger attraction for the electrons and pulls them closer to itself. I think we'll add that. So this is tug of war when there's a team that is significantly stronger than the other team, and they're just able to yank that flag closer to them and win the match. Okay, so we also have to think about the fact that these electrons are now spending more time, they're closer to the oxygen atom, and the electrons are negatively charged. In an ionic compound, when the electrons are completely transferred over to the nonmetal gets a negative charge because it's gained electrons. In this case, the oxygen has kind of gained the electrons. It hasn't completely gained the electrons because they're not totally transferred to itself, but the electrons are closer to the oxygen than they are the carbon. And so the oxygen gets slightly negatively charged. It's called a partial charge. I think I'm going to actually write it down here. So if we draw our carbon and our oxygen with our electrons closer to the oxygen becomes partially negative. And that's just the symbol delta. It's my terrible version for the partial symbol negative. So oxygen becomes partially negative because the electrons are closer to the oxygen. It's not a complete transfer, so it's not a complete negative charge. But the carbon, who now has kind of lost some electrons, becomes partially positive. It's not a complete positive charge because it's not a complete positive charge because the electrons haven't been completely transferred. So our carbon becomes partially positively charged because it's partially lost the electrons, and the oxygen is partially negatively charged because it's partially gained the electrons. So this unequal sharing results in partial charges. This is really important because it's these polar bonds that actually are responsible for some of these properties that we're seeing in our alcohol. If we have some atoms, and I think I'm going to change that word to molecules. So if we have molecules that have polar bonds in them, they can make much stronger intermolecular forces. Those are those attractive forces between particles that we talked about when we looked at properties of hydrocarbons. So if there's stronger intermolecular forces, they need more energy to separate the molecules from each other. And that means that the temperature has to be higher for the compound to melt and boil, so we get an increased melting and boiling point. So that's why when we compared our properties for ethane and ethanol, it's almost 100 degrees difference in melting point and boiling points between the two of them. It comes down to the fact that this oxygen has a much stronger attraction for the electrons and pulls the electrons closer to itself and creating this polar bond. And now that we have this polar bond in our molecule, it can make stronger intermolecular forces. All right, so if we want to be able to predict some more properties of our substances, we want to know if our molecule is going to have some polar bonds or some non-polar bonds. So we're going to focus in on determining whether or not electrons are going to be shared equally or not equally. And then we'll come back another day and look at these stronger intermolecular forces and how they're forming differently than the London dispersion forces we have seen before. So just hit pause, make sure you have this copied down, and then we'll move on. All right, we're going to determine if electrons are shared equally or unequally. So if we want to figure out if electrons are shared equally or unequally, one of the things, I'm going to backtrack. Different types of atoms have different amounts of attraction for electrons, and there's a lot of factors that come into play that result in this varying level of attraction. We're not really going to get into them, but this ability to attract electrons is called electronegativity. Okay, so it is a ability of an atom to attract electrons. If it's it's numerical, and so if it's the higher the number, the stronger the attraction. Now, if we want to know if our electrons are going to be shared equally or unequally in a bond, we look at the electronegativity difference. So what is the difference between the two atoms' ability to attract electrons? In our situation between carbon and hydrogen, they both had about an equal attraction to the electrons, but when we compared our carbon and our oxygen, they had a significantly different ability to attract. So if you want to know, if you are looking for the numerical value for electronegativity, you need to look at your periodic table. Okay. So I have our periodic table right here. And if you look on this side, right up kind of in the legend, it's hard to see on mine, but right here it says electronegativity. So that very first number, actually maybe I'll zoom in here. That very first number underneath the atomic number is underneath the atomic molar mass is the electronegativity value. That still doesn't look awesome. Okay. Here we go. 2.1. That looks worse. Great. So hydrogen, if you look, has a electronegativity value of 2.1. If we come over here and we look at our carbon way over here, carbon is you're going to see it on your periodic table, it's 2.5. So there's not a lot of difference between 2.5 and 2.1. Okay. So their attraction for electrons is about the same. But if you look at oxygen is a 3.5 in electronegativity. So the difference between a 2.1 and a 3.5, that's quite a big difference. So oxygen has a significantly higher electronegativity value. So it is pulling the electrons towards itself. So if you want to predict or figure out if there is a polar bond or a non-polar bond, you look at the difference in electronegativity. So we're gonna maybe write that out, and I think I'm gonna scroll up so I have a nice bit of space here, and I'm gonna say electronegativity difference. So this is a little bit of just a little bit of a scale to show you what the electronegativity differences tell you. If the electronegativity difference is less than or equal to 0.4, you have a nonpolar covalent bond. If the electronegativity difference is greater than 0.4, not greater than and equal, just greater, and less than 1.7, then you have an unequal sharing and partial charges. And if the electronegativity difference is greater than 1.7, that's when we get an ionic bond and a complete transfer of our electrons. So just before we finish off, I want to do a couple examples with you where we are looking at our electronegativity difference. And we're going to start off with a couple we already know, carbon and hydrogen. Ugh, stupid pen. So carbon has an electronegativity difference. We looked at our periodic table of 2.5. And hydrogen was a 2.1. I've got to hit pause and clean this up. So if we look at the difference, 2.5 subtract 2.1 equals 0.4. So 0.4 is in the nonpolar range. So this is a nonpolar covalent bond. All right, let's look at oxygen and hydrogen. If we look at our periodic table, oxygen is 3.5 and our hydrogen is 2.1. So we do the math, we do the subtraction, 3.5 subtract 2.1, and we get 1.4. Maybe. Kind of. All right. So this is greater than 0.4, but less than 1.7. So this is a polar bond. And I'm just going to write polar because my pen is being awful. And let's do one more. You are going to go and find the information for carbon and chlorine. And actually, you can do this one too. Nitrogen and hydrogen. Okay, so hit pause, find the electronegativity values for these two examples, and determine if they're going to form a polar bond or a nonpolar bond. Okay, so chlorine is an electronegativity of 3 and carbon is 2.5. So that gives us a difference of 2.5, giving us a polar bond. And nitrogen is a 3.0 and hydrogen is 2.1. And that gives us a 1.9. Now you're going to say, oh, Miss S, if it's over 1.7, it's ionic. But these are usually the cases. We know that nitrogen and hydrogen cannot be ionic because it does not have a metal and a nonmetal. Now, the last thing you have to do and remember when you are dealing with polar and nonpolar bonds is that if you have a polar bond, you have to give it partial charges. So our oxygen has to get the partial negative sign. Our hydrogen gets the partial positive sign. Same down here. Chlorine is the bigger number, so it goes partially negative, and our carbon are partially positive. And so if you were drawing it to look like they were bonded together, sorry, I kind of messed this up, but you'll get it. Nitrogen and hydrogen are bonded like this. Nitrogen becomes partially negative, and our hydrogen becomes partially positive. Okay, so that is an awful lot of information for you, but it's important to recognize that the reason this oxygen causes such a difference in properties all comes down to the fact that the electrons are shared differently in the bond.